Multivariate classification. When x is in R to the d, if the class conditional densities P of x conditioning on Ci are taken as normal density and d of mu I sigma I, we have that P of the class conditional density P of conditioning x conditioning on Ci is equals to 1 over 2 pi to the d over 2 times the absolute values of a sigma I to the 1/2, then times to the exponent of minus 1/2 times x minus mu I to the transpose times the sigma I inverse times x minus mu I. The main reason for this is its analytical simplicity. Besides, the normal density is a model for many naturally occurring phenomena in that examples of most classes can be seen as mildly changed versions of a single prototype mu I, and the covariance matrix sigma I denotes the amount of noise in each variable and the correlations of these noise sources. While real data may not often be exactly multivariate normal, it is a useful approximation. In addition to its mathematical tractability, the model is robust to departures from normality, as is shown in many works. However, one clear requirement is that the sample of a class should form a single group. If there are multiple groups, one should use a mixture model. Let us say we want to predict the type of a car that a customer would be interested in. Different cars are the classes, and the X are observable data of customers. For example, age and income. Mu I is the vector of mean age and income of customers who buy car type I, and sigma I is their covariance matrix. Sigma I1 to the square and sigma I2 to the square are the age and income variances, and sigma I12 is the covariance of age and income in a group of customers who buy car type I. When we define the discriminant function as gi of x equals to log of p of x conditioning on Ci plus log of p of Ci, and assuming p of x conditioning on Ci is approximately by the normal distribution ND of mu I sigma I, we have that gi of x is equals to, after we taking the log, that will be minus d over 2 times log 2 pi minus 1/2 times log of the absolute values of sigma I minus 1/2 times x minus mu I to the transpose times sigma I to the inverse times x minus mu I, then plus log p of Ci. Given a training sample for k which is greater than or equals to 2 classes, x is equals to the set x to the transpose R to the transpose, where Ri to the transpose is 1 if x to the transpose is in class I and 0 otherwise. Estimates for the means and the covariances are found using maximum likelihood separately for each class. That is, p hat of Ci is equals to the summations of Ri to the t, summing for index t, then divided by n. Mi is equal to the summations of Ri to the t times x to the t summing for index t, then divided by the summations of Ri to the t summing for index t. Si is equals to the summations of Ri to the t times x to the t minus mi times x to the t minus mi to the transpose, summing for index t, then divided by the summations of Ri to the t summing for index t. These are then plugged into the discriminant function to get the estimates for the discriminants. Ignoring the first constant term, we have gi of x is equals to minus 1/2 times log of the absolute values of Si minus 1/2 times x minus mi to the transpose times Si to the inverse times x minus mi, then plus log of p hat of Ci. Expanding this, we get gi of x is equals to minus 1/2 times log of the absolute values of Si minus 1/2 times the following terms: x to the transpose times Si to the inverse times x minus 2 times x to the transpose times si to the inverse times mi plus mi to the transpose times si to the inverse times mi. Then plus log of p hat of ci, which defines a quadratic discriminant. See figure 5.3. That can also be written as g of x, which is equals to x to the transpose times wi times x plus wi to the transpose times x plus wi0, where wi, the first wi for it is x transpose times wi times x, is equals to minus 1/2 times si to the inverse. The second wi, which is in the term in j of x of wi to the transpose times x, this wi, is equals to si to the inverse times mi. The third term, wi0, is equals to minus 1/2 times mi to the transpose times si to the inverse times mi minus 1/2 times log of the absolute values of si plus log of the p hat of ci. The number of parameters to be estimated are k times d for the means and k times d plus 1 divided by 2 for the covariance matrices. When d is large and the samples are small, si may be singular and inverses may not exist, or the size of si may be non-zero but too small, in which case it will be unstable. Small changes in si will cause large changes in si to the inverse. For the estimates to be reliable on small samples, one may want to decrease dimensionality d by redesigning the feature extractor and select a subset of the features or somehow combine existing features. We discuss such methods in Chapter 6. Another possibility is to pool the data and estimate a common covariance matrix for all classes. That is, S equals to the summations of p hat of ci times si, summing for index I. In this case of equal covariance matrices, equation 5.19 reduces to g of x equals to minus 1/2 times x minus mi to the transpose times s to the inverse times x minus mi, then plus log of p hat of ci. The number of parameters is k times d for the means, and d times d plus 1 over 2 for the shared covariance matrix. If the priors are equal, the optimal decision rule is to assign input to the class whose means Mahalanobis distance to the input is the smallest. As before, unequal priors shift the boundary toward the less likely class. Note that in this case, the quadratic term x to the transpose times x to the minus 1 times x cancels, since it is common in all discriminants, and the decision boundaries are linear, leading to a linear discriminant, figure 5.4, that can be written as g of x is equals to wi to the transpose times x plus wi0, where wi is equals to s minus s to the inverse times mi, and wi0 is equals to minus 1/2 times mi to the transpose times s inverse times mi, then plus log of p hat of ci. Figure 5.3 shows us classes have different covariance matrices, likelihood densities, and the posterior probability for one of the classes, top. And the class distributions are indicated by isoprobability contours, and the discriminant is drawn on the bottom. In figure 5.4 are the covariances may be arbitrary, but shared by both classes. Now, decision regions of such a linear classifier are convex, namely when 2 points are chosen arbitrarily in one decision region and are connected by a straight line, all the points on the line will lie in the region. Further simplification may be possible by assuming all off-diagonals of the covariance matrix to be 0, thus assuming independent variables. This is the naive Bayes classifier, where the probability of xj conditioning on Ci are univariate Gaussian. S and its inverse are diagonal, and we get g of x equals to minus 1/2 times the summations of the square of xj to the transpose minus mij divided by sj, and plus the log of p hat of ci, where the summation is summing for index j starting from 1 to d. The term xj to the t minus mij, then divided by sj, which is in the first term of this gi of x, has the effect of normalization and measures the distance in terms of standard deviation units. Geometrically speaking, classes are hyperellipsoidal, and because the covariances are 0, are axial aligned. See figure 5.5. Figure 5.5 means that all classes have equal diagonal covariance matrices, but variances are not equal. The number of parameters is k times d for the means and d for the variances. Thus, the complexity of S is reduced from big O of d squared to big O of d. Simplifying even further, if we assume all variances to be equal, the Mahalanobis distance reduces to Euclidean distance. Geometrically, the distribution is shaped spherically, centered around the main vector mi. See figure 5.6. Then the absolute values of S is equals to S to the 2d, and S to the inverse is equals to 1 over S2, then times the identity matrix. The number of parameters in this case is k times d for the means and 1 for S squared. Gi of x is equals to minus of the square of x minus m mi, then divided by 2 times s squared, plus log of p hat of ci, which is equals to minus 1 over 2s squared times the summations of xj to the t minus mij to the square, plus log of p hat of ci, summing with index j starting from 1 to d. If the priors are equal, we have g of x equals to minus of the square of the value of x minus mi. This is named the nearest mean classifier because it assigns the input to the class of the nearest mean. If each mean is thought of as the ideal prototype or template for the class, this is a template matching procedure. This can be expanded as g of x equals to minus of the square of x minus mi, which by definition is equals to minus of x minus mi to the transpose times x minus mi, which is equals to minus of x transpose times x minus 2 times mi to the transpose times x plus mi to the transpose times mi. The first term, x transpose times x, is shared in all g of x and can be dropped. Figure 5.6 means that all classes have equal diagonal covariance matrices of equal variances on both dimensions. Okay, we have discussed about the first term of this x transpose times x is shared in all g of x and can be dropped, and we can write the discriminant function as g of x equals to wi to the transpose times x plus wi0, where wi equals to mi and wi0 is equals to minus 1/2 times the square of mi. If all mi have similar norms, then this term can also be ignored, and we can use g of x is equals to mi to the transpose times x. When the norms of mi are comparable, dot product can also be used as the similarity measure instead of the negative Euclidean distance. We can actually think of finding the best discriminant function as the task of finding the best distance function. This can be seen as another approach to classification. Instead of learning the discriminant functions, g of x, we want to learn the suitable distance function d of x1, x2, such that for any x1, x2, x3, where x1 and x2 belong to the same class and x1 and x3 belong to two different classes, we would like to have d of x1, x2 which is less than d of x1, x3.